We have it set up to record to the cloud, so Jamie can pull it down later on.
Say that again. What to the cloud?
I said I've got the record going, so it's going to the cloud. In other words, it's going to go to the recording that you can access.
Right. Sorry.
Okay.
Wifey just handed me food, so I just.
All right, there we are. Well, good morning, everyone. We're going to be starting a little early this morning. We have a different sort of event than we normally do. Hugh Ross will be teaching, start straight away in about a minute, and then go till about 11:10, after which he has another appointment that he has to go and teach at. Ross Hoagland will be taking over after that. I'll be working with Ross Hoagland on that, but Ross Hoagland will be the primary instructor afterwards. We will be taking the Q&A that we took last week and holding it over. So we won't be able to answer the questions from last week, some of which are excellent, and some of them look like they're going to take a little bit of time to respond to. So we'll hold those for next week, presuming that Hugh will be here next week the same way. And with that, I will turn it over to Hugh Ross now. Hugh, please, it's all yours. You open us in prayer, and then it's all yours.
I'll be happy to do that. Father in heaven, we thank you for this time you've given us this day. It's a wonderful day. It's Valentine's Day, and you're the one that really showed love to us. So thank you for the Valentine's card of giving us the Holy Scriptures, as well as the universe and the earth in which we can enjoy life and see your revelation. And Father, I just pray that this day you'd give us the capacity to see how your book of nature and your book of scripture really do integrate and sustain one another. Lord, I pray that you'd bless my teaching time as well as that of Ross Hoagland and the team that we've got assembled here. In Jesus' name, amen. Yeah, I just found out a few days ago that I'm scheduled to do a virtual seminar in Alabama within about 40 minutes from now. A little less than 40 minutes actually. So yeah, we've set up a special thing here where I'm going to basically teach until I have to exit. And then Ross has got a really good message for you. Yeah, he has prepared a review of Michael Denton's latest book. It's a great book. Several of us at Reasons have read it. So I'm really appreciative that Ross has set up to do a review of that. And what I'm going to do now is share screen. Because I have a scientific discovery here that's gotten an incredible amount of press attention and a lot of confusion too. And so I want to take you through that. I introduced it very briefly last week. And let me jump into this. Yeah, here we go. Okay, you should all be seeing my first slide. This is just simply a reminder. I do take questions on Facebook and Twitter, so feel free to visit me there and take advantage of the 24/7 YouTube channel that Reasons to Believe has set up for you. The series we're in right now is on God's two books, the Book of Nature and the Book of Scripture. And I deal with that in detail in this book more than a theory. And you can get a free chapter at reasons.org/Ross. We also produced years ago this docudrama on a dual revelation. It's a DVD, and you can get that at the store at reasons.org. And we're not going to be doing a Zoom meeting this time. We're going to stay in the webinar throughout. We'll set that up for next week. So we'll just pass that through. But the news is all about what's happening and what astronomers have found in the upper atmosphere of Venus. And, I've written about this, and you'll find an article on our reasons.org website under questions from social media, where somebody asked me, where is the most life-friendly site in the solar system outside of planet Earth? And the most life-friendly site is indeed the upper atmosphere of Venus. I mean, everybody's thinking that Mars is the best place, but you actually got more hospitable features for life on the upper atmosphere of Venus than you do for the Earth. and it's about 50 to 65 kilometers above the surface of Venus. And what we notice there is that that height above the surface of Venus, you got the same temperature as what exists at Earth's surface and the same air pressure. And so atmospheric conditions, at least the physical conditions, are the same as what you have on Earth. And so astronomers for decades now have been speculating maybe there's microbes in the upper atmosphere of Venus. Now, what has tempered that a little bit is that we know the atmospheric composition. Astronomical spectroscopy tells us that the atmosphere of Venus, both the lower and the upper atmosphere, is about 97% carbon dioxide, 3% nitrogen, and trace amounts of sulfur dioxide and sulfuric acid. Now, when we talk about trace amounts, it's not the same as what we see on the Earth. Venus is an atmosphere that's 92 times thicker than that of the Earth. And so the quantity of sulfur dioxide and sulfuric acid is such that it makes the atmosphere highly acidic. The carbon dioxide contributes to that as well. And so this is what's dampened enthusiasm for the possibility of life in the upper atmosphere of Venus. Look at all the sulfuric acid. Reminds me of a little quick poem that my chemistry teacher in high school taught us, which was, there was a boy named Moore who drank something. I'm messing up the joke. I'm not even going to try it. But what he thought was H2O was H2SO4, and he wound up dying. Yeah, there was a boy named Moore who is a boy no more, for what he thought was H2O was H2SO4. Highly deadly, very deadly acid, and therefore people said there's really no way there could be life there. Another problem is there's no magnetosphere around Venus, which means there's nothing to stop deadly radiation from the sun and deadly radiation from cosmic rays from coming in. And the other problem is Venus is quite a bit closer to the sun than the Earth is, and therefore it receives a much stronger dose of ultraviolet radiation. And that too would pose a problem for life. Nevertheless, the upper atmosphere of Venus indeed ranks by far as the most life-friendly site outside of planet Earth. And what generated all the excitement was back in September, a team of 19 astronomers said, we have found phosphine in the upper atmosphere of Venus. And what they found was, here we go. They published the results in September of 2020, and they said we have found 20 parts per billion by volume of phosphine in the upper atmosphere of Venus. And they basically said, we think this is a signature for life, and it's actually generated within 1 month 4,700 news stories around the world. It's now over 5,000 news stories that have been propagated as a result of this discovery. But what is not in these news stories is that this was all started by a paper that actually was published online in the January of 2020, and then published in Astrobiology in their February issue by a team led by Sousa Silva. And basically they're arguing that phosphine is a biomarker, that if we can find phosphine in the atmosphere of a terrestrial planet, that would be an indication there's life on that particular planet. Now, this paper is not cited in any of the news articles I'm aware of. In fact, it was hardly mentioned. I mean, you do see a footnote, an endnote in it, in the paper that was published claiming 20 parts per billion. But I went and read the paper, and when you look at the paper, they make the point, well, phosphine's already been discovered on planets in the solar system. In Jupiter, it's 4,800 parts per billion by volume, and Saturn is 15,900 parts per billion by volume. But what they explained in that paper was that these are gas giant planets. And being gas giant planets, the temperature is much higher in the deep interior of the atmosphere of both of these planets than it is on the surface. In fact, it's hotter than 800 Kelvin. And they made the point that if it's hotter than 800 Kelvin, you're going to get the production of considerable amounts of phosphine abiotically. You don't need life. If you got a temperature that high and you got phosphorus on the planet, it's inevitable you're going to get a significant amount of phosphine. I'll give you the chemical formula for phosphine. It's basically phosphorus with 3 hydrogen atoms attached to it. And their point was on both Jupiter and Saturn, in fact, any gas giant anywhere in the universe, you're going to have phosphine showing up in the upper atmosphere, because what happens is the phosphine produced at these deep, high temperature areas, interiors of these planets, will rise up. And you won't get as much phosphine, but you will get significant phosphine remaining in the upper atmosphere. And that explains why you got such high levels of phosphine in Jupiter and Saturn. But back in that paper was published in January of 2020, they were saying, now, wait a minute, we're talking terrestrial planets. And unless the terrestrial planet has a very hot surface temperature, you're not going to get the production of phosphine unless it's being produced by life. On the other hand, the surface temperature of Venus is close to what you need to get the production of phosphine. The mean surface temperature of Venus is 737 Kelvin. So we're talking just 63 degrees away from being able to produce it. And that's the mean temperature. And so this is not brought up in any of the papers, but as I read the papers, I said, it certainly seems feasible that there would be spots on the surface of Venus that would depart by the mean enough that you could actually be producing phosphine abiotically. And actually, if you read the paper that was published in September of 2020, they do make the point that there are several different ways that you can get phosphine without having to have that high temperature. And they focus on the point that we already know there are anaerobic microbes on Earth that emit phosphine. Not a lot, but they do emit phosphine. The biggest source of biotic phosphine on the Earth is when you get the decay of dead organisms. So organisms, and a wide variety of organisms, when they die and their organic matter decays, you get the release of phosphine. And on planet Earth, you also get a lot from industrial plants that are producing fumigants because phosphine is deadly for certain life forms. That's used, for example, to get rid of mice and rats. And so they said, well, that's another source. And then there's a variety of source ways of getting phosphine abiotically at cool temperatures. But these are very complex and would produce at most just tiny amounts of phosphine. So in the September 2020 paper, the 19 authors said, we don't think it's at all likely that you're going to be able to get any phosphine at cool temperatures abiotically on Venus. Maybe, certainly you could do it with the complex chemistry going on the Earth, but not on Venus. And therefore they concluded the phosphine they found at 20 parts per billion is a signal that life, or the remains of life, exists in the upper atmosphere of Venus. And when I read that paper, I recognized, now wait a minute, the remains of life are bound to be in the upper atmosphere of Venus because of how close Venus is to planet Earth. I mean, Earth every day is expelling microbes, particularly diatoms, into interplanetary space. And that's being deposited on all the solar system bodies. The moon, you're going to have a lot there, Mars and Venus. So Venus should have a significant amount of the remains of microbial life on Venus. Some have even speculated that viable life from Earth could be in the upper atmosphere of Venus. Personally, I don't think there's a very high probability at all that life from Earth could be viably transported to Venus. It has to cross interplanetary space, And unless it crosses that interplanetary space very quickly, it'll be dead by the time it gets to Venus. On the other hand, that can't be ruled out. There is a possibility that it could be ejected from Earth by meteoritic impacts on a rapid pathway to Venus, particularly when Venus is close to the Earth. So yes, there is a possibility you could actually have viable microbes from Earth in the upper atmosphere of Venus. However, once it gets there, it's not going to live long because of the ultraviolet radiation, and also because of the sulfuric acid that exists there and the acidity you get from the carbon dioxide, and just the radiation you get from the sun and from cosmic rays. So it's really the remains that I think is going to be the point. This would generate all the excitement, is that, hey, Venus has been harboring at least the remains of life on there. Now, as far as what phosphine actually looks like, this is its chemical formula: one phosphorus atom with 3 hydrogen atoms attached to it. You would think this would be fairly easy to construct, but typically you need high temperatures, and only the ones I mentioned that can do this at cool temperatures. So that's what phosphine looks like. Some of its physical properties: it's colorless, it has no odor, it is flammable. In fact, it's highly flammable. And the problem with phosphine on Earth, particularly plants that are making fumigants, is that they're releasing significant quantities of phosphine. Phosphine is heavier than air, and so it settles down. And when it settles down into low regions, say around the factory that's producing this stuff, or for that matter, around regions where you've got anaerobic microbes that are expelling phosphine, that can settle into low areas and reach concentrations where it could self-ignite. And people talked about ball lightning, and this has been one suggestion is how to explain these short ignitions that take place in low-lying cavities on the surface of the Earth. And anaerobic microbes are able to tolerate phosphine, but no animal. In fact, advanced plants are also a danger. It's highly toxic to animals. At 50 parts per million, it's lethal to animals, and you get significant health consequences starting at just 0.3 parts per million or 300 parts per billion. So this is something you don't want to be around. And what really generated well, let me go to this next slide here. September 2020 is when you had a team of 19 astronomers, and incidentally, this team of 19 included 2 of the astronomers that were part of the paper was published in January 2020, where they said, hey, we think phosphine could be a biosignature. And it was that paper that basically launched a study. And so astronomers took the 2 most sensitive millimeter wave telescopes that existed and began to look at Venus. Venus is really the first place they looked, because they said this is the area, the one planet where we think we got the best chance of finding phosphine on a terrestrial planet. And the paper generated a lot of enthusiasm. They said we found the phosphine, and it's at 20 parts per billion by volume. On the other hand, it was just 1 month later that another team of astronomers, an independent team, said, give us the data. And that was one good thing about the 19 astronomers. They made their data publicly available. So an independent team took the identical database and used their analysis and said, well, using what we think is actually a superior analysis technique, and we get an upper limit. We're not finding phosphine. And in fact, we establish it can't be more abundant than 3 parts per billion by volume. And so that kind of put a damper on all these news stories that were going out. And the same team that published in September 2020 came back and said, well, we're going to do some infrared measurements. They said, we think that millimeter wavelength spectral lines are the best place to find phosphine, but another way we can get an independent check, there is a spectral line at infrared wavelengths. So they did some telescope observations at infrared wavelengths, published a report and said, we didn't find phosphine. The upper limit is 5 parts per billion by volume. And basically they were saying, unless there's highly variability of phosphine on Venus, which is certainly possible, then we must have overestimated our phosphine discovery by about a factor of 4. And they actually followed that up in November of 2020. And in that paper, they claimed that they had found phosphine at 1 to 4 parts per billion by volume. Now, when you're getting down to 1 or 2 parts per billion, that's at the observing limit of the telescopes. And so, but basically they're saying, they're making the claim, we found the phosphine, but it's at least 5 times less than what we claimed in September. And so they're using the same, they basically went through the data again and basically said, yes, we agree, we made some mistakes in the data analysis, and we're now only claiming 1 to 4 parts per billion. But that's right at the level of the measuring limit for the telescope. And then a third independent team jumped in December 2020 and basically went over the analysis again using a completely different method and basically said, we find less than 3 parts per billion by volume. And just a couple of days ago, a paper was published where they said, we find 0 evidence for phosphine, and they're basically looking at the same data set that was produced in September of 2020. And what's interesting about all 5 of the papers that have been published on this since September 2020, all of them are saying we need to do more observations. We need to, in fact, back in January 2020, the team that was suggesting phosphine said only the James Webb telescope will have the possibility of definitively establishing whether there's any phosphine in Venus, because the James Webb telescope, well, the capability of measuring the abundance of phosphine in Venus to just a fraction of a part per billion by volume. So it's much more sensitive than the instruments we have right now. And yesterday I actually got to see the James Webb telescope. It's housed at Northrop Grumman in Redondo Beach, California. So a friend of mine who's an engineer there let me come in and take a look at it. It's an amazing instrument to see. And they now have a firm launch date. It's going to be launched October 31st of this year. And it'll begin producing astronomical data within about 6 months after that. They have to kind of get it set up and tested and calibrated. But once that happens, it'll start producing results. And incidentally, I've read several hundred papers in the astronomical literature all saying, hey, if we just had the James Webb Space Telescope, we could establish this kind of discovery. So there's going to be a huge amount of demand on that telescope once it becomes operational. And it's going to be situated 1 million miles away from the Earth. Say, why so far? Well, that's a place where you're at a Lagrange point. I won't go into the technical details, but it's where you can have the telescope at a very stable distance from the Earth. And it's a way where they can get greater pointing accuracy than they can with a Hubble Space Telescope. So it's one feature that's going to make it much more productive. And so that's kind of where the situation stands now. But the bottom line is all this excitement about the discovery of phosphine has basically gone away. The research that's happened over the past 5 months basically tells us, well, we thought we found phosphine, but we really haven't. At best, we got an upper limit, and the upper limit seems to be a hard upper limit that there's no more phosphine on Venus than 3 parts per billion by volume, and there could be none at all. And the latest papers in December and February also make the point, if you actually look at the chemistry of the upper atmosphere of Venus, any phosphine that is being generated there will be quickly destroyed. On the other hand, we got a lot of the remains of life in Venus. You could actually still have 1 part per billion, even with the chemistry that's going on there. And you say, well, what about Earth? Well, that's what's interesting too. Phosphine on Earth. Uh, uh, Nowhere in Earth's atmosphere, except near industrial fumigant production plants, is there phosphine even approaching 10 parts per billion. So here's Earth. Earth is flooded with decaying organic material. We got dead organic material decaying all over the surface of the Earth. We have, quadrillions of anaerobic bacteria producing phosphine, and Earth's atmosphere is not destroying phosphine anywhere near the level that would be happening on Venus, and yet we can't even measure 10 parts per billion by volume. On the other hand, people have not really done definitive searches. And so there's a call out there, okay, let's actually use the satellites that are orbiting the Earth and see if we can actually make a hard measurement. What we do know is that the upper limit is 10 parts per billion by volume, and it could be a lot less than that. And you say, what's the bottom line here? Well, the bottom line is that what we've seen over the past 15 years is people claiming to find the signature of life in different parts of the universe, and then later along the line withdrawing it. Probably the most famous example is about 15 years ago, there was a paper published saying, we have found glycine, the simplest of the bioactive amino acids, in a dense interstellar molecular cloud. And a good decade afterwards, they said, we misidentified the spectral line. And so the claim for glycine being discovered has been withdrawn. Unfortunately, there's still a lot of textbooks out there claiming that we have found interstellar glycine. The answer is we thought we did, but we didn't. And a little bit later than that, a paper was published in the Astrophysical Journal claiming that they had found a nucleobase in the same dense interstellar molecular cloud. But again, about a decade later, that claim was withdrawn where they said we misidentified the spectral line. These complex molecules generate lines that are difficult to discern from other lines. And so this is just a third example of that where they said, well, we thought we found phosphine, but it looks like we really haven't. Now, I don't want to be too skeptical on this. I've been on public record. We will inevitably find interstellar glycine. We will inevitably find interstellar nucleobases. And I think we will find phosphine in the upper atmosphere of Venus. It's just that it's not going to be at the quantity levels we've been measuring right now. One reason why I'm convinced we're going to find glycine in interstellar molecular clouds, we know the chemistry there operates to produce glycine. The problem is you also got chemistry in the same interstellar molecular cloud that destroys glycine. So you're not going to find it at parts per million. And right now, that's about the measuring limit of trying to find glycine in interstellar molecular cloud. It's running at around 100 parts per billion. And when we get the technology to find, as I say, 1 part per billion, I'm predicting we will find glycine. After all, it's an amino acid with only 10 atoms in it. So that's the simplest by far of the amino acids. And I'm convinced we will find it, but we're not going to find it at a high abundance level. And at 1 part per billion, that's way below the concentration you would need for there to be any possibility of assembling naturalistically amino acids to make even the shortest protein molecules. And keep in mind, this is the simplest of the amino acids. Likewise, I'm on record as saying, I think inevitably we will find a nucleobase, maybe all 4 or 5 of the nucleobases, interstellar molecular clouds. They're not that complex. And once we get the capability of finding the abundances of, say, a part per billion, I think we're going to find it. But once again, abundance levels of 1 part per billion are going to be of no value for naturalistic origin of life models. They need concentrations much higher. Likewise, I think there's a good chance that there will be phosphine in the upper atmosphere of Venus. If for no other reason, we know there's a lot of the remains of Earth life in the upper atmosphere of Venus, and as that decays, it will produce phosphine. The ultraviolet radiation, the cosmic radiation, the acids in the upper atmosphere are going to work to destroy that phosphine. So we're going to find it at a very low abundance level. It wouldn't surprise me if we find it at 1 part per billion or a fraction of a part per billion. That's about what we'd expect, given the fact that, and incidentally, if there's hot spots on the surface of Venus, that's going to produce phosphine, and that's going to waft up into the upper atmosphere of Venus. But again, as it gets in there, a lot of it's going to be destroyed by the chemistry that's operating there. That's kind of the bottom line here in terms of life signatures. I see a lot of papers published where people are saying, hey, look at how we, if there's life, it's going to produce this. And, there's ways that the chemistry can make this. On the other hand, there's chemistry that works to destroy it. You have to look at the production rates as well as the destruction rates to get an idea how much you're going to see and where it's coming from. And so I don't think right now we have a single reliable chemical life signature for life outside the solar system. I think the best one we got is ozone. If we find ozone, that's a good signature that you're going to have molecular oxygen. And if you got a lot of molecular oxygen, that's also a signature you might have life. On the other hand, watch out. If you've got a planet with significant plate tectonic activity on it, that's going to produce oxygen without life at all, just like it happens here on planet Earth. Our deep the deep carbon cycle and water cycle on planet Earth produces oxygen thanks to the strong plate tectonic activity. So the bottom line is we have to be careful about this. Well, let me give a brief introduction. I'll tell you what, before I jump in to our series on dual revelation, I'll take a few minutes for questions that you might have on this phosphine discovery. So let me exit the the share feature here, and we'll go back. Here we go. So if there's a few questions on the phosphine, I'll take them. If they're not, I'll jump into giving an introduction and see how far I get on the dual revelation before I have to exit.
The questions that have come in so far were not on phosphine. There was one about the NASA Mars Perseverance astrobiology rover, and what do you expect it to find after it lands this Thursday?
Yeah, I could answer that question. Yeah, that's another attempt to try to find whether or not there's signatures of life on Mars. And one reason why I focused on Venus is actually a better option in terms of trying to find life or the remains of life than Mars is. I mean, we have lots of evidence that Mars has conditions that are not conducive to life. And I think one thing that NASA is overlooking is just how much sulfur is on the surface of Venus or of Mars. We're talking about the problem of sulfur on Venus. Mars has got way more sulfur than Venus has. To give you an idea, the surface of Mars has 60 times as much sulfur as the surface of the Earth. And so if you ever saw that movie, The Martian, where it shows Matt Damon scooping up Martian soil and using it to raise potatoes, you're not going to raise potatoes on Mars with Martian soil. The sulfur guarantees that you're not going to get anything growing there. And but the amount of sulfur there also means that's not going to be conducive for life. Although what this particular spacecraft is interested in is whether or not there's subterranean life. I mean, scientists already realize we're talking the surface of Mars. There's no way life is going to survive there. There's no magnetosphere. And so there's nothing to stop the cosmic radiation. or the solar radiation. The ultraviolet radiation is going to be a problem, but they're thinking maybe below the surface. And what's, I think, driving the whole thing is that we know that below the surface of Mars in certain locations, you've got frozen water. And if there's activity going on there that warms that water up, you could have liquid water. And then, the NASA mantra has been, where you got liquid water, you might have life. But liquid water is only one of many requirements for life. Keep in mind, if you got liquid water there, it's going to mix with the sulfur. You're going to get sulfuric acid. So I don't think there's going to be any possibility of finding underground water simply because of the sulfur content that's there.
Okay, there are no other questions on the phosphine.
Okay, tell you what, let me go to share screen and we'll get started. Here we go.
You've only got a couple of minutes, though, Hugh.
Okay, I got to be fast then, because then I got to cut out and do my event in Alabama. Okay, dual revelation. This is a hallmark of reasons to believe that we're persuaded by scriptures, particularly Psalm 19 and Romans 1, that God has revealed himself faithfully in a trustworthy, reliable manner through two books, the book of scripture and the book of nature. And the ministry of reasons to believe has been taking the book of nature that's been exposed to the entire population of the world and use that as a tool to bring people to the book of scripture and to discover Jesus Christ and help them develop a relationship with Jesus Christ and be set free from their sin and their evil. And this is a book I'd like to recommend. It's a 4 views book that I participated in. It involved the presidents of BioLogos, the Discovery Institute, Answers in Genesis, and I was in there as the president of Reasons to Believe. 4 views on creation, evolution, and intelligent design. And there were 2 features of this book that I think are significant for what we're talking about right now. One is that we all talked about what we thought about biblical inerrancy, and also what we thought about the 2 books doctrine, the idea that God has revealed himself through 2 books. And what's interesting is that all 4 presidents had distinct views, both on biblical inerrancy and also on the revelation of God through 2 books. They all claimed to believe in biblical inerrancy. They all claimed to believe in the 2 books doctrine, but when it got to be, hey, Kate, tell us specifically what you think this is, it was radically different. I don't have time to go into the details, but you can read the book and see for yourself where the 4 different organizations stand on that particular issue. Another book that you can get, it's a much more detailed book than the previous book, and it's a 2 views book. It's basically a discourse between BioLogos and Reasons to Believe, involving multiple authors from both BioLogos and Reasons to Believe, and was moderated by Southern Baptist theologians. And so the Southern Baptist theologians briefly posed questions, and then a representative from Reasons to Believe and BioLogos would respond. And so this is where you can see a really detailed difference between what's referred to as evolutionary creationism and the old earth day age model of Reasons to Believe. And both of these books are available in the Reasons to Believe store. So you can go there and get the 2 books there. And then the different models. And there's actually 6 models I'm going to discuss, but the different models for integrating the 2 books fall into these 4 basic categories. And one is that only one book is reliable, the other book is not. That's called the conflict model. And you can guess which organizations support that idea. There's a separate magisterium model that there's no conflict between the 2 because they're addressing totally separate magisteria, totally separate subjects. Then there's a complementary model, which is basically the idea there are the two books, but they hardly overlap at all. And then there's a constructive integration, which says that they do overlap, but there's a wide range of how much overlap occurs. Okay, with that, I'm going to stop the share feature because I'm thinking it's time for me to exit and move on to my event in Alabama. I'll be with all of you next week, and I'm going to turn it over to our team here. And Ross, I hear you've got an exciting event for us on a review of the latest book by Michael Denton. And what's interesting is Michael is not a believer. On the other hand, he's an enthusiastic supporter of reasons to believe. I've had a chance to meet him personally, and what's interesting is the issues that's holding him back from being a Christian faith, but it's not the science issues. When it comes to the science, he really sees a strong support for what we believe and reasons to believe. So
Hey,
that,
where does the link where you're going to go to? What is your Alabama presentation going to be today? Where, like, do you have the link for it? So if people want to follow it, they can do it.
I'm not sure it's a public event.
Okay.
So I know it's a church in Alabama. They've had Fuzz in to speak. They're having me in to speak today. And I would provide the link, but it's a link that allows you to take control of the meeting. And I'm not supposed to give that out to the general public. So,
Okay. All right. Well, have a good time, Hugh, and
right.
bless you in your meeting there.
Thank you.
All right.
And,
Take care.
All right. You too. Okay. Bye-bye.
Thanks. So for right now, we're going to continue the webinar, but we're going to continue with Ross Hoagland, who's going to be talking specifically about Michael Denton's new book, which is faithful to the fine-tuning argument that Hugh talks about very frequently. So with that, I'm going to turn it over to Ross Hoagland. If during Ross Hoagland's presentation you have any questions for Ross Hoagland, we will take those questions, and I'll be monitoring the Q&A. So Ross, go ahead and take it away. And if there are any questions pop up, or I have any questions for you, I'll intervene. How's that?
Yeah, thank you. Thank you, Mark. And I would want to say thank you to you for giving me the opportunity to do this. And Mark, if there's any questions that are just so excellent, they shouldn't wait till the end. Let me know and I'll take them. So
I'll be happy to.
My PowerPoint, this is the book. It's Michael Denton. He's a fellow at the Discovery Institute, The Miracle of the Cell. It came out late last year. I saw him on a YouTube video, and I read it about 3 months ago, and I was so excited about this book. I'm going to try to do the screen share now. I put together a basic PowerPoint on this. So give me... Somehow I wound up at the very end. Miracle of the Cell. Okay. I was really excited about this book because it talks about fine-tuning from a standpoint that's a little bit different about fine-tuning than Hugh Ross usually gets into. He was talking about it from the standpoint of chemistry and biochemistry. And for anybody that's out there, Hugh Ross talks a lot about fine-tuning, but I've never heard him define it. And I came up with a little definition. Fine-tuning is the observation that certain characteristics of a system have values or characteristics that must be within a narrow range for that system to function properly or at all. And I think a really good example would be, as the name fine-tuning implies, I've always assumed that that came from the old analog radios where you had to turn the knob very carefully to get the station. And if you remember, any of you that are as old as I am, the cheaper the radio, the harder it was to get the station. You had to be very careful. So, Hugh talks a lot about fine tuning, brightness of the sun, the mass and the gravity of the earth have to be just right for life to exist. In this book, Michael Denton talks about the fact that there are 28 elements from the periodic chart that are used by at least one living species. He describes several and their fitness of the elements and compounds themselves for certain biological systems. Now, one of the things he said that I thought was really interesting is that none of the material that he covers in the book. And any of the claims he makes about the chemistry or the biochemistry are in any way controversial. These are all things that are accepted by anyone who knows anything really about the field. He loves to use the word fitness rather than fine tuning. Hugh likes fine tuning. Michael Denton talks about fitness. He's talking really about the same thing. And these elements have characteristics that make them fit for life. And the thing that really struck me is that these characteristics are present from the initial creation of each element. Some of them, like hydrogen, were created in the Big Bang, and some of them were created later on in generation 1 and 2 stars. But as soon as the element was created, it's just like it was now, and it has characteristics that make it fit for life that are very finely tuned. So I want to start with a quote that really kind of sums up where I want to go with this. Just as the letters of the alphabet have the potential for endless surprise and enchantment, so too do the elements of the kingdom. Unlike an alphabet which has hardly any infrastructure, the kingdom has sufficient structure to make it an intellectually satisfying aggregate of entities. And because these entities are finely balanced, living personalities with quirks of character and not always evident dispositions, the kingdom will always be a land of infinite delight. That's from Peter Atkins in The Periodic Kingdom. So I thought it would be fun to go into some examples. He goes into probably 20 different elements and compounds and why they're fit for life. I'm going to try to do about 3 of them. Start with carbon. That's the one that you always hear, that everything is carbon-based life, and it's essential for all life. Carbon is one of the few compounds that easily forms long and complex molecules. Now, this blew me away. The number of carbon compounds is estimated to be almost 10 million different compounds on Earth. There are all the other compounds known on Earth don't amount to that much, even with all the other different elements. Of all the elements, only carbon can form strong bonds with itself to form chains of almost unlimited length. It can create chains with itself and other kinds of atoms as well. So that allows it to make molecules, biomolecules that are over 1 million atoms in size. And if you think about it, those kinds of long chains would be essential for life. Relate it to, I think about a computer program. If you limited a computer program to a certain number of lines of code, or you would severely limit how much the program can do. It's likewise with life. Some of the systems are so complex that it's going to require really large molecules to get the job done. And carbon is the only element that is able to do that. Carbon is what's called tetravalent. What that means is that each atom of carbon can form up to 4 other bonds with other carbon atoms and other atoms used in biochemistry. So the ability to make really complex molecules is built in right from the beginning. Now, the bonds need to be extremely stable so that they don't fall apart from motion and radiation and all the things that are going on in a cell. And because carbon has a small atomic radius, it's only number 6 in the periodic chart, those bonds can be extremely stable. Its strength and energy level are fit for life. If the strength of the bonds were any weaker, the molecules would be unstable and they would fall apart. If they were stronger, then the bonds wouldn't be able to be broken for rearrangement as needed in the cell. and there would be no controlled chemistry. That they call that metastability. And here's the amazing thing, that metastability is in the same temperature range that water is a liquid, and it matches with Earth's ambient temperature. There's no reason for that. You think of some metals, for example, iron. What would iron be like in its liquid form? Well, we don't know because it's not in its liquid form on Earth's ambient temperature, so we can't really judge it that way. Also, carbon has unique directional nature of the bonds that it has with other atoms. So to sum it up, carbon it forms stable bonds with itself. It forms up to 4 bonds. It's tetravalent, has multiple bonds with itself and other atoms. Its energy level is fit for biochemical manipulation, and it's metastable in the same temperature that water is a liquid. It's pretty amazing that all of those features are there. Any one of them, if it was different, life would not exist as we know it. And I'll close this little section on carbon with another quote. The book had so many good quotes in it. I could have just taught this from quotes. We see, therefore, that carbon is perhaps the most unique in its physical and chemical properties of the whole series of the elements. And so far as the evidence points, it seems to exist for the one purpose of rendering the development of organized life a possibility. It further appears that its unique chemical properties, in combination with that of the other elements which constitute protoplasm, have enabled the various forms of life to produce the almost infinite variety of substances adapted for man's use and enjoyment, and especially to serve the purposes of his ever-advancing research into the secrets of the universe. Alfred Russel Wallace from The World of Life. In the last part of that quote, it's pretty amazing if you look at that. He's acknowledging that not only is carbon necessary for life, but also the dead life, which gives us oil and gas and gypsum and marble and granite and all of that stuff that we use that is derived ultimately from biological material. So let's go to water. Water is not an element, obviously, it's a compound, but there are some special things about water that make it uniquely suited for life. And I'll start with another quote. Water is the most important liquid for our existence and plays an essential role in physics, chemistry, biology, and geoscience. What makes water unique is not only its importance, but also the anomalous of many of its macroscopic properties. If water would not behave in this unusual way, it is most questionable if life could have developed on planet Earth. From Anders Nilsson and Lars Peterson. So let's get into some of the specific things that water can do. Water molecule is polar, and that simply means that it has a negative charge on one side and a positive charge on the other. And that's part of what makes it a universal solvent. Water will dissolve pretty much anything to some degree that it comes in contact with. It's why it makes it so corrosive for things like iron. But that feature is necessary for what goes on in the cell. Now, the one thing that water is not good at dissolving, it is not a solvent for hydrocarbons. Hydrocarbons are what make up the body of the cell, things like proteins and cell walls. And so what happens is you get this natural separation of material. Hydrocarbons in an aqueous environment tend to cluster together and makes it much easier to form things like cell walls and proteins. The solubility and insolubility of certain things causes that separation chemically. Water also has a certain viscosity, and you think viscosity is just the thickness of a liquid. Think of trying to drink water through a straw as opposed to drinking a milkshake through a straw. Milkshake is more viscous. Then try to think of drinking honey through a straw. The thicker the liquid, the more energy it would take to draw it up through a straw or a capillary. If viscosity of water was any higher, it would require too much energy to draw it through capillaries and other places in the cell where it travels. If it was any less, too much energy expended to move it. Another thing that water has is a diffusion rate. If you dissolve something, put a drop of something, food coloring, in a bucket of water, there's a certain rate at which that coloring will travel all the way through the water. That diffusion rate is absolutely necessary for biological systems. If the diffusion rate were any less, the cells would need to be smaller so that the material in the water would get to the cell just as quick. And if they were smaller, they would be less complex. And one of the places where viscosity and diffusion rate came to light in the book that I thought was really fascinating is in capillaries. Capillaries, of course, are really the smallest blood vessels in biological systems. The vessels come from the heart and they get smaller and smaller and smaller. They turn into capillaries. Capillaries are only 5 microns across. They permeate all the tissues in the organs, and they're what carry blood enriched with oxygen, which is then diffused into the cells. Oxygen, of course, provides the energy to the cells. Now, in mammals, there's about 1,000 capillaries per square micron. The capillaries are about 40 microns apart, and this is the part that I thought was really fascinating. Most cells in a mammal are only 1 to 3 cells distant from a capillary. So you can imagine that if the viscosity, which controls the rate at which water can flow and how small a capillary it can flow through, and then the diffusion rate, which controls the rate at which the oxygen would leave the blood cell and get into the regular cells, if those two numbers were any different, you would not get the oxygen to the cells. And if the viscosity or the diffusion, if the viscosity was any higher, the capillaries would have to be much larger, and there'd be no room for the tissues that the capillaries supply. It would all be capillaries. Another thing about water is, I mentioned this a little bit before, it's a universal solvent. It dissolves almost in anything. And there's a quote that I want to read out of the book. When I put my PowerPoint together this morning, to be honest, I ran out of time and couldn't type all this stuff out. This is from Philip Ball. He says, water plays a wide variety of roles in biochemical processes. It maintains macromolecular structure and mediates molecular recognition. It activates and modulates protein dynamics. It provides a switchable communication channel across membranes and between the inside and outside of proteins. Many of these properties do seem to depend to a greater or lesser degree on the special attributes of the H2O molecule, and in particular, its ability to engage in directional weak bonding. Thus, although it seems entirely likely that some of water's function in biology are those of a generic polar solvent rather than being unique to water itself, it is very hard to imagine any other solvent that could fulfill all of its roles. Now, one of the things that I thought was really fascinating was this idea that water can work with what's called a protein wire. Think of an electrical wire where an electron goes in one end of the copper and comes out the other end. Water actually can form long chains of linked water molecules for moving protons around the cell. It's like a pipe. Think of a pipe with a whole bunch of ping pong balls in it. If you push a ping pong ball in one end, the ping pong ball is going to fall out the other end immediately. It's not the same ball, but the action is immediate. So another quote about that that's really fascinating. He says, other charged particles involved in cellular functions have to move themselves physically from one place to another. Protons can pass their energy along a hydrogen bonded water wire without moving themselves at all, thanks to this so-called Grothus mechanism. A proton attaches to one end of the wire, and in a split second, each of the hydrogen bonds further along the length of the wire spin around in sequence so that a proton drops off the water molecule at the other end of the wire instantly. The initial proton is not moved any further than the starting end of the wire, but its charge and energy have been conducted along the wire's length. And this is with water. You think of it, it's easily to think of that as with a physical wire made of copper or silver, but this is a liquid. This amazing liquid, water, can't be part of a biological system in frozen or gas form, and it just so happens that it is liquid, thus available for biological systems at the same temperature range as the ambient temperature on Earth. Again, that didn't have to be that way. Our warm-blooded nature depends critically on the thermal properties of water, its high heat capacity and high latent heat of evaporation. If those were any different, we could not function the way that we do. He goes into quite a long chapter on metals that are used in biological systems. The one that I thought was the most interesting was magnesium, so I wanted to talk about that. Magnesium, I didn't know this, is in every cell type in every organism. It is also in ATP. Adenosine triphosphate is the major molecule conveying energy in the cell. There's no other element besides magnesium that is suitable to work in ATP. The most interesting part of magnesium, though, is the fact that it is in chlorophyll. Magnesium plays an irreplaceable role in capturing sunlight. Listen to this quote, another quote from Peter Atkins. Without chlorophyll, the world would be a damp, warm rock instead of the soft green haven of life that we know. For chlorophyll holds its magnesium eye to the sun and captures the energy of sunlight in the first step of photosynthesis. Magnesium has exactly the right features to make this process possible. Had the kingdom lacked this element, chlorophyll's eye would have been blind, photosynthesis would not take place, and life as we know it would not exist. Peter Atkins from the Periodic Kingdom. The light absorbing power of magnesium and its low loss of energy as it's operating approaches the theoretical limit for conversion of light into electrical energy. I want to read that again because that is astounding. How could that occur in a biological system without direction, without guidance? Let me read it again. Light absorbing power of magnesium and its low level of energy loss approaches the theoretical limit for conversion of light into electric energy. So those are three of the elements that and compounds that he talks about in the book. He's got a couple of dozen overall that he does. And I highly recommend the book. It's easy to read. Mark says it's a well-written book. He looked at it, and I agree. I'm not a chemist, and I was able to understand it pretty well. I kind of want to sum this up in my own words. It's really easy to think of chemistry how I've always thought of it as being kind of dry and not too interesting or inspiring to see each element with only a few characteristics. But in this book, Michael Denton brings out the fact that there are sometimes dozens of characteristics of each element and compound, and some of them are just downright odd, kind of like people. If many of these dozens of characteristics in the 28 elements used to one degree or another in biological systems weren't just as they are, life like we know it just wouldn't exist. Now, this is really a powerful apologetic. I want to touch for a minute on the apologetic argument with this. These characteristics that allow for life in elements and compounds used in biology were built into these elements at their very formation. Again, some of them at the Big Bang itself, some of them were made later on in later generations of stars. But anyone who understands this has to account for that fact. And you're really faced with two possibilities. The atheist, the naturalist, is going to say, it's just dumb luck. That's the way it worked out. We can't know why that is. Or a creator who would have had to have been outside of the universe, endowed matter with these characteristics and abilities. And it's very interesting that if a creator, the characteristics of that creator would have to be very close to what we believe is the Christian God, someone with mind and will and purpose and the ability to create with this, with biology in mind. Now, one of the questions that a skeptic might ask, another one would be, well, this is really just one kind of life. Maybe there's other kinds of life that we can't even know about. I think there's a good response to that. First is a negative argument. There's no evidence anywhere that there is any other kind of life other than carbon-based life. The other is more of a positive argument, and that is that only carbon, out of all the elements, can form the stable and complex bonds that any life would seem to require. And that would limit the type of life that would be possible to, there's a whole lot of limits that would create. Certain temperature range, gravitational range, pH range, and that's just what we happen to have on planet Earth. I read somewhere about, what about a life form that's based in gas rather than liquid and solid? Well, the problem with that is gas is all mixed together, and you can't have life if you don't have discrete sections of cells that do different things, and that would be impossible with gas. So think when you come across that argument, and I've heard it many times, the best answer is to say that given the data as we currently understand it, in other words, we don't get to hypothesize or guess at what's going to come. Given the science as we understand it now, there's no possibility for life in any kind of foreign environment. Many of you have probably heard the phrase better living through chemistry. I looked it up, it was a sales pitch by the DuPont company in 1935, and in the 60s and 70s, it was kind of a phrase used by the counterculture for drugs. Well, I want to paraphrase that. I want to say better worship through chemistry. I had an experience, personal experience a few weeks ago after having read this book and one other book about biology. I was sitting out in my garden enjoying the sunshine, pulling some weeds, and I sat down and started looking at the trees and the plants. And at the same moment, I was seeing the absolute stunning beauty of the sunshine through all of these amazing living things, and more acutely aware of the absolute miracle of how the cell works. And I had a little God moment. There's no other way to describe it. I was just suddenly really aware of how attentive he was to me and to everyone who can enjoy this. And I was praising him and thanking him and enjoying sitting in the sun. And I sat there for better than an hour, just taking it in, taking him in. Reminds me of the verse, the heavens above declare the glory of God, and the sky above proclaims his handiwork. I want to paraphrase that. Think about that word glory. It's such a religious word. I've heard this verse 8,000 times, and you don't think of what that means. And the heavens declare the amazingness of God, the creativity of God, the beauty of God. The heavens declare the sense of fun that God has. The heavens declare the love of God. The heavens declare the playfulness of God, the wisdom of God. There's so many words that fit in there. And I was really enjoying all of that at that moment that I had out in my garden. And since then, I've just been much more aware. I try not to miss the beautiful sunshine that we have here in Southern California and all the living things around me. And I'm just more acutely aware of how God has done this for me. I take it very personally. He did it for Ross. He did it for me. And of course, for each one of us. One more verse that obviously applies. Psalm 139, I praise you. And that's what I was doing. For I am fearfully and wonderfully made. Wonderful are your works. My soul knows it very well. My frame was not hidden from you when I was being made in secret, intricately woven in the depths of the earth. I want to close my little talk here with a quote from a poem by William Blake. To see the world in a grain of sand and a heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. Well, that's my talk, and I'd be happy to try to take questions, even though I'm no expert on this. I would love to hear from anybody who wants to say anything.
We do have one from Mark Durham. He says, I'm presently taking RTB's class advanced seminar on biochemical design. For those who are interested in this subject, I highly recommend taking this course. And that would be the Reasons Institute course. Many biological evolutionists appeal to an imaginary fourth law of thermodynamics. Carbon and other elements tend to form complex molecules and eventually life, despite the second law of thermodynamics. Do you have any thoughts on this imaginary fourth law of thermodynamics?
I think it's really important that when we're debating this or discussing it, we have to keep it focused on the science as we currently understand it. Everything else is just conjecture. Is what they're saying scientific? And the only way to answer that is to stick to what we know right now. And we don't know anything about that fourth law. Isn't it just as likely to say it was created by a conscious, powerful being? And I think the evidence for creation is a whole lot stronger than appealing to a possible unknown hypothetical fourth law. Here's the way I look at it, and I've kind of come up with this idea myself. We know the characteristics of designed things. We can look at something in our environment, and usually we know if it was something that man designed or if it was produced by a natural system. And one of the ways that we intuitively know that is that we know that designed things have a specific arrangement of parts that can't be produced by a natural system. A really simple example is a ring of granite stones around a fire at a campsite. If you walk up to a clearing in a field and you see a ring of stones, you never think, gee, some natural process created that, the rocks rolled off the hill and they just happen to form a ring. You know that it must have been done purposely, because natural processes, it's so unlikely to produce that. And right now, given the science as we understand it, it looks like biological systems are arranged in a certain way that cannot be done by any kind of natural process. It so resembles designed things that it is reasonable and really a scientific deduction that it was produced by consciousness and not a natural process of any kind.
Ross, when I was thinking about that fourth putative or hypothetical or speculative law of fourth law of thermodynamics that Mark Durham brought up, which I think is an excellent question, by the way. Thank you, Mark Durham. Is that when I've looked at some of the responses to that from both theistic and non-theistic scientists, and one of the interesting things that most of them share is that if you're going to invent a hypothetical law of thermodynamics, that you have to explain how that law of thermodynamics would work with the other three laws of thermodynamics. And there's absolutely no explanation for that. Some of them even said it borders on crazy because the other laws do such a perfect job explaining and predicting that they couldn't imagine why they would need anything else other than this hypothesis or speculation in order to save this other idea, which is that these chemicals will self-organize in ways that are unfathomably complicated. So even the so-called naturalist groups look at that putative fourth law and say, first of all, we don't see it anywhere. If the only place that it exists is in some place that you'll never know how to find it, then how do we know it's not anything other than just magic? You're just using that as a term to gloss over magic or this unknown force. And if it's an unknown force, why isn't that a God force? And these are atheists saying this. They're saying, you're come up with something that's not any better than the creationists are coming up with. So that it's interesting that when you see an entire discipline, for example, evolutionary biology, bumping up into a very, very difficult or what seems like an intractable problem, which is exactly the problem you were talking about today, which is how do you have all of these chemicals working together in precisely the same way, any other way than having them finely tuned? And you come up with a speculation, that means that your idea that only chemistry is the answer is in a crisis. That when you have to go out and start coming up with imaginary things, you are in a crisis because you're not using science. So I think that's at least I would say that that's part of the answer that might be responsive to Mark Durham.
Yeah, to me, it just brings out their absolute commitment to naturalism way beyond what is warranted. I think it's always good to look for a naturalistic explanation of things first. But at what point do you say, well, maybe this just doesn't work anymore? Why is the God hypothesis any less likely than some unknown hypothetical fourth law of thermodynamics?
Yeah, that is a problem, and it's a bigger problem because an unknown law has to, in order for you to come up with this unknown law and posit it, is that you have to say it does something that none of the other laws will explain, and there is some way to test it. And the so-called fourth law has no way of being tested, and that's one of the problems. It ends up being just explains everything, but because it explains everything, it explains nothing, because any explanation that you provide for it, it just says, well, it's the fourth law that did it.
Right.
Thank you for the label of mystery by using a fourth law. We have some other questions though. Let me go into the question mode here. From Norm Helgeson, do you recall the property of magnesium that makes it so essential and included in every cell?
Well, one of them is that it has a unique ability to respond to light. And that's why it's part of the photosynthesis mechanism. It also there was one other, and to be honest, I don't remember it. Let me go back in my notes. I just that it's part of the ATP molecule, but I don't remember what it is about the ATP molecule and magnesium that made it so unique. I remember in the book he says that calcium is very similar to magnesium in many of its characteristics, but that magnesium does a big job with ATP, and so that's what's used in ATP. But I'm sorry, I don't remember.
You mentioned earlier that it was sensitive to light and converted light into removed electrons in a very, very efficient rate, almost
right
to the absolute theoretical rate that it could possibly be done.
Yeah.
It seems that if magnesium had that function in the cell and worked that way to facilitate photosynthesis, that one of the answers to the property of magnesium is its photovoltaic effect, is that it has this extremely efficient photovoltaicism. So it can move these electrons very quickly from sunlight, and without that, you don't have photosynthesis and you don't have life.
With a real low loss of energy in the process. That's what was amazing to me.
Yeah, thank you for that. Johnny asks, is there a specific mechanism behind the appearance of these proton pump water chains?
Is there a what?
Is there a specific mechanism behind the appearance of these proton pump water chains?
I don't have enough knowledge of biochemistry to answer that question.
Okay. Tim Williams asks, does Denton propose possible sources for the miraculous cell, or does he just leave that as an open-ended question?
No, he's not a Christian, but he leaves open two possibilities. Number one, that there is a natural physical law that someday that we will discover that can account for all of this. Or he says it's possible that God exists and that this truly was all set up from the very beginning. And I think reading between the lines, I think he leans towards the latter. He uses a lot of teleological language in the book. It's clear that he's sympathetic to that argument. Really, how do you think otherwise if all of this stuff is built in from the very beginning and there's no other life to exist? That's a pretty strong argument.
Indeed. So I don't see any other questions popping up. Let me look in the chat for a second, see if there's anything else. Okay, that looks like it, Ross. I think you've done a masterful job here.
Well, thank you. What do you think? Do you have any questions, Mark, or comments, or?
No, I think that the only thing I would get at would be the importance of the argument itself, which is the importance of the fine-tuning argument, and that if we're going to defend the existence of God from fine-tuning, that alone isn't going to solve the problem, because there are other explanations for the fine-tuning. The three best explanations, or the three explanations that are rational, is one, that it's just an accident, a primitive accident, that it just the entire universe just happened this way. So that's one not irrational answer for the existence of these very finely tuned laws and constants and outcomes, particularly in biology. The other one is that there is a multiverse, and that in each bubble of this multiverse are all of these different possibilities, one of which landed where we are. There are problems with that, just like there are some interesting ideas that make it a little bit more reasonable than some people might think. But so that's the second one. And the third one is that you have the divine designer, that the reason everything is so precisely designed for life is that there's a designer who did it. So if we have these three possibilities, the question is, number one is the first one, which is this is just a brute fact, that the universe just is this way, it just was always like that, and that we just have to live with it. We don't need a designer to explain it. Is that really an answer, or is that a cop-out? And I think that's a cop-out, because it does is it says, well, we've bumped into a question that we as scientists can't answer. Therefore, we won't. Yet, if you're really going to be honest about your inquiry, you have to ask, well, are there other possibilities? Well, then you have the two others that remain. Now, the big question is, if you're going to say that it's just a brute fact, and then fold your arms and be indifferent, and say, well, we're not going to go any further than that, are you even being scientific when you're doing that? That almost sounds like a God of the gaps argument.
Yeah.
Well, it's just there, therefore it's just there.
Because that God of the gaps argument works both ways. I call it naturalism of the gaps. That's what they do. They just fill it in with a naturalistic explanation, even if that naturalistic explanation is pretty far-fetched.
Yeah, and so we as Christians have something that neither the multiverse theorists have, or the what I would call the primitive accident theorists have. And that is that we have an accumulation of other evidence that testimony to the existence of God, other than just that you have a very finely tuned universe and finely tuned life. And so as Christians, we should use the fine-tuning argument, recognizing that it's not the end of the question. That there are other things that have to get explained in this world that cannot be explained strictly by mechanical means. For example, as Ross has talked about in the past, things like intelligence, consciousness, the origin of life, the origin of humanity, and other origins that aren't easily or even possibly explained by pure chemistry. And then you have also the question of good and evil, the question of the existence of beauty. How do we even understand what beauty is? Communication, and on and on and on. I don't want to get us into a new webinar here. But the point is that we have this enormous constellation of facts and ideas, all of which associate to a cumulative argument for the existence of God, that one part of which is the fine-tuning argument. And we ought not to rely on fine-tuning exclusively when we have just so many other things. And the fine-tuning becomes much more beautiful in that regard.
Mark, I have a question for you. From a philosophical standpoint, that first option, the idea that that's just the way things are, how far, from an intellectual honesty standpoint, how far can you take that argument? I mean, let's say for the next 100 years, we just keep discovering more and more features of the universe on every level that appear fine-tuned. Is there some point at which the atheist should be able to say, okay, I give up, this is just too much? Or can you just make that, is that a valid argument forever?
Well, it's not really a valid argument. What it is, it's a speculation. So what they're doing is they're evading argument. What they're doing is saying, well, if it just is, then there's nothing else to be said. There's nothing else to be said about a designer. There's nothing else to be said even about a multiverse. If what is just is, it's as if it's eternal and there is no need for it to be explained.
Mm-hmm.
There's no argument. There's just a claim to brute fact. Philosophically, that is tenable. Philosophically, you can say, well, all right, is it logically possible? Yes, it is logically possible. It is logically possible that you have an eternal universe and that it was eternal in the sense that it somehow, who knows how, possessed these features that ended up where we are now. The big question is how, and the person who holds to the position that these brute facts just exist is going to have to say, well, let's just, okay, give me 10 billion finely tuned things. I'll just tell you that we're all there in the beginning. And so since that's just the way it is, this isn't unexpected. We might even expect more of these interesting things. Let's keep looking. So that's the philosophical point. The philosophical point to be made about that is it is not by itself an argument, it's a claim. And it's a claim to avoid arguments.
So I guess the best question to ask would be then, why do you believe that? Ask an atheist, why do you believe that it's just a brute fact?
Yes, that would be a good question. And the question that should follow that is, if there are other explanations, why would you be indifferent to them?
Right, because science, they tell us, is all about endless inquiry. It sounds like they're putting up the white flag at that point.
It does, because if science is really there to explain or predict phenomena, then merely claiming a brute fact and saying, well, we don't want to explain that or characterize it beyond just saying it's a brute fact is not the way science works. That by definition, that would not be a scientific claim.
Right, interesting.
Yeah, it is. It very much
They're
is.
avoiding their own subject.
Yeah, fortunately, there are not a lot of people who hold that position, but there are some who do, and they will typically migrate if they're atheist or not theistic, because not everybody's an atheist who doesn't, they're not hostile atheists. They can just say, I don't know. They will migrate to the multiverse theory because at least that gives them some hope of an explanation that doesn't require a designer, because then the question will always go back to, well, who designed the designer and that kind of thing,
Yeah.
which is a really good thing to get into. But those are arguments that we should be ready to engage.
Are there any other questions, Mark? I see a couple of questions. Do they apply?
Yeah, let me get my official question glasses on here. Oh, wrong place. Oh, Norm Helgeson says, Marie Ann says, great presentation. I agree. That's
Thank
Norm
you.
agreeing. Thank you very much, Norm.
Thank you, Norm.
Is there a specific mechanism behind the appearance of the proton pump chains? Okay, that was one that we couldn't answer earlier.
Yeah.
So I think that's it, Ross. I think you're at 12:05 right now, and we have no other questions. So congratulations. It's very, very well done.
Thank you. Well, let's let everybody go home and
Okay, I just want to let everyone know that next week there is a possibility that Hugh will be doing the same thing again. That's a possibility, but it's not inevitable. So if next week you show up and we have the same thing where Hugh teaches for a little bit and somebody else comes in at the end, please understand that's because some of the events pop up very suddenly and Hugh doesn't have a chance to announce it. But as of right now, he will be here next week. And the questions that were posed last week and this week that did not get answered, I've recorded them and will pose them next week for Hugh. So fear not, the questions that were posed that did not get answered today or last week, we'll pose them again. So with that, thank you very much, everybody. Thank you very much, Ross, for taking the time. Great job on that. Bless you all. Have a great week.